From the physics book, Big Ideas Simply Explained. Heat can be a cause of motion. Heat engines. In context, key figure Sadi Carnot, 1796 to 1832. Before 50 CE, hero of Alexandria builds a small steam-driven engine known as the Aeolipile. 1665, Robert Boyle publishes An Experimental History of Cold, an attempt to determine the nature of cold. 1712, Thomas Newcomen builds the first successful steam engine. 1769, James Watt creates his improved steam engine. After 1834, British-American inventor Jacob Perkins makes the first refrigerator. 1859, Belgian engineer Etienne Lenoir develops the first successful internal combustion engine. It is hard to overestimate the impact of the coming of the steam engine in the 18th century. Steam engines gave people a previously unimaginable source of power. They were practical machines built by engineers and were put to the use on a grand scale to drive the Industrial Revolution. Scientists became fascinated by how the awesome power of steam engines was created, and their curiosity drove a revolution with heat at its heart. The idea of steam power is ancient. As long ago as the 3rd century BCE, a Greek inventor in Alexandria called Ctesibius realized that steam jets out powerfully from the spout of a water-filled container heated over a fire. He began to play with the idea of an aeolipile or wind ball, a hollow sphere on a pivot. When the water within boiled, the expanding steam escaped in jets from two curved directional nozzles, one on each side. The jets set the sphere spinning. About 350 years later, another Alexandrian named Hero created a working design for an aeolipile, replicas of which have since been built. It is now known that when liquid water turns to vapor, steam, the bonds holding its molecules to each other break down, causing it to expand. Hero's device, though, was simply a plaything, and although various inventors experimented with steam, it was another 1600 years before the first practical steam engine was built. The breakthrough was the discovery of the vacuum and the power of air pressure in the 17th century. In a famous demonstration in 1654, German physicist Otto von Guericke showed that atmospheric pressure was powerful enough to hold together the two halves of a sphere drained of air against the pulling power of 8 strong horses. This discovery opened up a new way of using steam, very different from Hero's jets. French inventor Denis Papin realized in the 1670s that if steam trapped in a cylinder cools and condenses, it shrinks dramatically to create a powerful vacuum, strong enough to draw up a heavy piston, a moving component of engines. So, instead of using steam's expansive power, the new discovery utilized the massive contraction when it cools and condenses. Steam Revolution. In 1698, English inventor Thomas Savery built the first large steam engine using Papin's principle. However, Savery's engine used high-pressure steam that made it dangerously explosive and unreliable. A much safer engine, which used lower-pressure steam, was built by Devon iron seller Thomas Newcomen in 1712. Although Newcomen's engine was so successful that it was installed in thousands of mines across Britain and Europe by 1755, it was inefficient because the cylinder had to be cooled at every stroke to condense the steam, and this used a huge amount of energy. In the 1760s, to improve on the Newcomen engine, Scottish engineer James Watt conducted the first scientific experiments on the way heat moves in a steam engine. His experiments led to his discovery, along with his compatriot Joseph Black, that it was heat, not temperature, that provides the motive power of steam. Watt also realized that the efficiency of steam engines could be hugely improved by using not one cylinder, but two. One which was kept hot all the time, and a separate cold one to condense the steam. Watt also introduced a crank to convert the up and down motion of the piston into the rotary motion needed to drive a wheel. This smoothed the action of the piston strokes to maintain constant power. Watt's innovations were extraordinarily successful and could be said to have launched the age of steam. Energy and thermodynamics. The efficiency of steam engines intrigued young French military engineer Sadi Carnot. He visited factory after factory, studying not only their steam engines, but also those driven by water power. In 1824, he wrote a short book, Reflections on the Motive Power of Heat. Carnot realized that heat is the basis of all motion on Earth, driving the winds and ocean currents, earthquakes and other geological shifts, and the body's muscle movements. He saw the cosmos as a giant heat engine made of countless smaller heat engines, systems driven by heat. This was the first recognition of the true significance of heat in the universe, and provided the launchpad for the science of thermodynamics. Seeing and comparing water and steam power in factories gave Carnot a key insight into the nature of heat engines. Like most of his contemporaries, he believed in the caloric theory, the false idea that heat was a fluid. However, this misconception allowed him to see a key analogy between water and steam power. Water power depends on a head of water, a difference in water levels that allows water to fall. In the same way, Carnot saw that a heat engine depends on a head of heat that allows a fall of caloric. In other words, for a heat engine to work, there must not just be heat, but also a cold place for it to flow to. The heat engine is driven not by heat, but by the flow of heat from hot to cold. So the motive power is the difference between hot and cold, not the heat by itself. Perfect efficiency. Carnot had a second key insight, that for the generation of maximum power, there must be no wasted flow of heat at any place or time. An ideal engine is one in which all the heat flow is converted into useful movement. Any loss of heat that does not generate motive power is a reduction in the heat engine's efficiency. To model this, Carnot outlined a theoretical ideal heat engine reduced to its basics. Now known as a Carnot engine, this ideal engine works in a cycle in 4 stages. First, the gas is heated by conduction from an external source, such as a reservoir or hot water, and expands. Second, the hot gas is kept insulated inside a cylinder, for example, and as it expands, it does work on its surroundings, such as pushing on a piston. As it expands, the gas cools. Third, the surroundings push the piston down, compressing the gas. Heat is transferred from the system to the cold reservoir. Finally, as the system is kept insulated and the piston continues to push down, the gas temperature rises again. In the first 2 stages, the gas is expanding, and in the second 2, it is contracting. But the expansion and contraction each go through 2 phases, isothermal and adiabatic. In the Carnot cycle, isothermal means there is an exchange of heat with the surroundings, but no temperature change in the system. Adiabatic means no heat goes either into or out of the system. Carnot calculated the efficiency of his ideal heat engine. If the hottest temperature reached is Th and the coldest is Tc, the fraction of heat energy that comes out as work, the efficiency, can be expressed as Th minus Tc divided by Th, which is equal to 1 minus Tc divided by Th. Even Carnot's ideal engine is far from 100%, but real engines are much less efficient than Carnot's engine. Unlike Carnot's ideal engine, real engines use irreversible processes. Once oil is burned, it stays burned. So the heat available for transfer is continually reduced. And some of the engine's work output is lost as heat through the friction of moving parts. Most motor vehicle engines are barely 25% efficient, and even steam turbines are only 60% efficient at best, which means a lot of heat is wasted. Carnot's work on heat was only just beginning when he died of cholera at the age of 36. Unfortunately, his copious notes were burned to destroy the infection, so we will never know how far he got. 2 years after his death, Benoit Paul Émile Clapeyron published a summary of Carnot's work using graphs to make the ideas clearer and updating it to remove the caloric element. As a result, Carnot's pioneering work on heat engines revolutionized our understanding of the key role of heat in the universe and laid the foundations of the science of thermodynamics.